So I'd like to welcome you back this afternoon to this very exciting occasion where we're celebrating 41 years since the publication of the original paper from David Cox. I'm Simon Thompson. I'm the current president of the British and Irish region of the International Biometric Society. So I just wanted to give you one or two bits of information about the Society and the future meetings which are coming up before we continue with the presentations today. The first is I know that because of the nature of the meeting, there are quite a lot of people here who are not members of the International Biometric Society. So if you have found this meeting very enjoyable and would like to join the Society, that would be excellent news, and you can do that via the website, and you get lots more information about the future meetings that are coming up and so on. One of the meetings that is the next one that's coming up is the Channel Network Conference, and this is the meeting where the four regions, I suppose, which do join the Channel, the Netherlands, France, Belgium, and the British and Irish region get together. And it's a conference that happens once every 2 years. It's been in every other country so far, and this is the first time that it's actually going to be in the UK. It's going to be in St Andrews from July the 3rd to July the 5th. And there are a number of invited sessions on genetics, genomic data, on mixed modeling, and on ecology, statistical ecology, with some very good keynote and invited speakers, including David Spiekerhalter, giving the Fisher Memorial Trust lecture there. The abstracts for oral presentations have actually closed, but you can still submit abstracts for posters, and you'll be able to do that until May the 1st, which is also the early bird registration deadline. So have a look at the website for the Biometric Society, have a look at the conference, and it would be very good if we could welcome a lot of you to that conference up in St Andrews in July. The next meetings, which are going to be in London, there's one in October, in statistical ecology. It's going to be a joint meeting with the British Ecological Society and the RSS Environmental Statistics section. And it's on species distribution modeling. That's going to be on October the 9th. And in November, at a date which hasn't quite been finalized yet, there's going to be a meeting on interoperability between different statistical software packages and how one can use the interoperability between packages to make advances and refinements in statistical analyses. That's for planning in November this year. Details will go up on the biometric website as soon as they're available. It'll be quite soon now. And the other thing I wanted to make sure that you're all aware of is that there is a prize given every 2 years for a young biometrician on the basis of a published paper, a paper they've published. Young in this context means within 5 years of completing full-time education, and the prize is worth £1,000, so not to be sniffed at. So if you think that you are a person who has such a paper that would be well received, then you should talk to your supervisor, mentor, or head of department, because it has to be nominated by somebody other than yourself. If you are the supervisor, head of department, etc., and you think you have a very good postdoc who's written an excellent paper that should be considered for this prize, do put them forward. You just have to write a very short covering note and include the paper, and the details of how to do that, again, are on the Biometric Society website. The closing date for that is the end of this calendar month, the end of March. And the only other thing I want to do in my introduction here is knowing that Daniel Farewell won't thank himself at the end of the meeting. He has done a fantastic amount of organisation for this meeting. He's led all the details, both the general details and all the very fine details of organising this meeting. And I'd just like if we could give Daniel a round of applause for having done that. So it's my pleasure now to introduce Torben Martinussen. He's Professor of Biostatistics at the Department of Public Health at the University of Copenhagen. As we've heard, that's an institute which is well known for their work in survival analysis, and particularly in the daunting area of counting processes and so on. He's an author of another daunting paper in JRSS-B on the topic which he's going to be talking about today, estimation of direct effects in survival data. But I was interested when I was looking at his website that he has a lot of collaborative publications in both medical aspects, medical collaborations, and in, I think, veterinary science as well. And so he spans both the methodological interests, which we should no doubt see today, but also a lot of applied collaborations indeed. So welcome to you. Thank you for coming from Copenhagen, and we look forward to your talk.
Yes, can you hear me? But not. Is the mic on? No. No. I thought I did it. Is it better? Yeah. Okay.
Can increase a bit.
So first of all, thank you very much for inviting me to this meeting. It's a great honor to have the chance to talk at this occasion. And it's right that I'm from Copenhagen, so you may think of me as one of the bad guys. So I will briefly mention parts of counting processes and also things that has shown to be, I think, quite important the last years, 10 years perhaps, about causality. So I'll speak about a special type within that area, namely estimation of direct effects. It's a joint work with Stijn Vansterland from Belgium. So a bit about my background is that I started in '92 as a PhD student at the Department of Biostatistics in Copenhagen, and at that time and during that period there was a lot of interest in survival analysis. My supervisor was Niels Keiding, and he and Per Krag Andersen had finished their book, or was just about to finish their book about survival analysis and counting processes. So I was an instructor when they taught courses in this area, so that was how I got into this area. And that at that point in time, the Cox model was still very dominating, and as we heard, it still is, and I think it is still the benchmark model when we do new developments in survival analysis. We always want to see how does this work for the Cox model. I think that's how it is. That said, I must say that it has had a tremendous impact on my scientific career, but I have actually been working on investigating other types of models, so competitor models to the Cox model. And one thing that I had focused on together with Thomas Scheike in Copenhagen is we have a book on dynamic models, so the theme is there how to estimate time-varying effects. So when the proportional hazards model assumption is questionable, can you do something different from what can be done within the Cox model, splitting up the time axis? But can you estimate time-varying effects in a more non-parametric way? And that's actually the model that I will also use partly today. It's the old additive hazards model. That's an additive hazard structure, which is very convenient when you want to estimate time-varying effects. Okay, but dynamic model is not actually the topic of my talk today. I'll mainly talk about how to try to estimate causal effects, and I'll explain or direct effects. I'll explain what I mean by that in a moment. Okay, so the theme is that we have an event time, capital T, we have an exposure x, and we have an intermediate variable k, and we would like to estimate what is the direct effect on our event time, so the effect not mediated via k. So at the end of my talk, I'll mention the problem of time-varying confounding, and this is in a way a start of solving, or at least giving a suggestion to that problem. So I will do the development based on the old model. I will show it in a moment, but at the end of my talk, I hope I will have time to as I said in the beginning, this is the benchmark model, so I hope I will have time to say something about how to do it within the Cox model. It is slightly more difficult to do it, surprisingly perhaps, in that model. Okay, so one inspiration for this talk was a paper by Cole and Anand in International Journal of Epidemiology, where they deal with this problem of direct effects. So the situation might be that we have our exposure, we have an intermediate variable, and we have a response. For the moment, I'll take y as a continuous response, so it's not a lifetime, but we'll deal with that later. So if this is the situation without the u, then one way of estimating, so here there is no direct effect. The effect of x on the response is via the intermediate variable k. So here it might be tempting just to control for k and then do the analysis, but the problem may then be that if there are some, or one or more than one unobserved confounders u, for the relation between k and the response, then conditioning on k will give us problems, because if you condition on k, you will open a path between x and u, and then you will see a false direct effect of x going via the unobserved confounders, and you will have problems. Then what you can hope for is that you may then collect additional information L, and L might be, or may be, multidimensional, so that the effect of the unmeasured confounders onto K goes via L. So that's the hope. So let's assume, and that's will be the setting that I'll be considering. So let's assume that that we can actually collect L so that the effect of u on k goes via L. If that's the case, then you can actually estimate the direct effect of x on y now, conditioning on L and k. So I did actually a simulation here where the true effect of x is 0. So if we have the unmeasured u, of course we get the right answer. We don't have u, but in this case, conditioning only on x, k, and L, you still get the right answer. So then it's smooth. But then if these variables, or one variable L, they are also affected by the exposure x, then you will have problems again, because if you condition on L again, you will again open a path between x and u, because L is a so-called collider, and you will get a spurious effect of x again going via the unobserved confounders. So then you still have a problem. And I did a simulation of this here. So again, if we know u, we get the right answer. There is no effect of x. But we don't see u, so if we condition on x, k, and L, we get a spurious effect of x here. So we get an incorrect estimation. Okay, what can then be done? So this is actually the setting that I will be considering, that I will assume this DAG, and I would like to estimate the direct effect of x, so the effect of x not mediated via the variable k. Can this be done? First of all, I think I need to explain what do I actually mean. Is there a precise definition of a direct effect? And here I will use this notation here. So I'll be interested in the distribution of y given what I call x hat and k hat. And that is actually the do intervention of Pearl and also the Robbins machinery that I will use. But I'll try to explain what that means. So behind this is something about causality. So the causal effect, or also called the total effect, is what you estimate in a randomized study. The theory behind, or why is this machinery about causality developed? One way of seeing it is that what if we have observational studies? Can we still learn something about exposure effects? So we don't have a randomized study. Yes, sometimes we can by using this machinery of causality. This is actually not the setting that I will deal with. I will actually assume that we have a randomized treatment, but I will be interested in this direct effect instead. Key references to this area is the work by Robbins. Difficult to read. You may know that if you have tried. So for many years I thought, I'll never understand this and it's not important. And maybe I still won't understand it, but I think it's important now. And another reference is, and using another notation is the book by Pearl, and actually I find that easier to understand. It gives you actually a way of calculating these distributions, which I will show you here. Whoops. So a brief introduction to the Pearl machinery is given here. So say we have this DAG and we want to estimate the causal effect of X on Y. Then what you do is that you have your joint distribution and you form the product of conditional distributions respecting your DAG. Then the distribution of all the variables Z1 to Z3 and Y given do X. So now we intervene on X. How can we construct this distribution? Well, if we intervene on X, there is no stochastics anymore into X. So this part of the distribution, the X given Z1 and Z3, is simply deleted because now we intervene on X. So this is a definition of this distribution, and if you want the causal effect on Y, you just marginalize over Z1, Z2, and Z3. This is a key formula, I think, in this area, because now we have a machinery to actually compute these quantities, and that's what I will use. Of course, how the specific expression of the formula is will depend on your DAG. So if I change my DAG, I'll get another formula, but the principle is the same. Form the conditional distributions respecting the DAG, and erase whatever distributions you have to erase when you intervene. That was quite fundamental, at least for me, to understand, because then I was then able to actually maneuver in this area. Okay, can we use this in this area? So this was the graph giving me problems before, because conditioning on L and K will open a path here. So I'll get a spurious effect of the direct effect. The distribution that I want to estimate is this one. So I want to intervene not only on X but also on K, because I want to change X, but I want to keep K fixed. So what I see there must be the direct effect of X. So this is the distribution that I want to study. And using this, it's called the G computational formula. So that's what you also had a reference to that, Bianca. So this is the G computation, and you can work it out. For this graph, it looks like this. So you have to have a distribution for Y given X, K, and L. That's just the observed distribution. But you also have to marginalize over L given X. So this is the G computational formula in this case. And this can be worked out. So this was, if we have a linear model here, and we have a linear model for L given X, then I can calculate this using the formula up here. And it's nothing but this expression here. And we can see that what's interesting is that here we have a direct effect of X. So it's not only gamma of X here. So that was the false estimate. There is a correction term which has to do with the effect of X on L and the effect of L up here. So that's the correction term. And in the example, we have these two estimates for gamma x and gamma L. So that's the model of y given x, k, and L. To use this, I need also to estimate this model. So if I estimate that model, L given x, I see that my phi x here is 0.5. And doing this little calculation, I'll get the right answer. So this formula will actually give me the right answer, that the direct effect of x is actually 0. So that's one solution using the so-called G formula. One needs to model y given x, k, and L, but also L given x. Another suggestion, which actually was the inspiration for the work that I will show you today, was a paper by Stein and some co-authors setting out how to do this when you have a continuous response. Their idea is that instead of using y as the response, we will use the residual where we take out the effect of k. So I will use y minus gamma k of k as the response. So I want to deal with this graph instead. So here there is no effect of k on y. And if that's the case, then the direct effect, the effect of x not mediated via k, is simply the total effect of x. So there you can take your residual here and just regress it on x. So that was the idea of this paper. So if I do that, so that's what I've done here. I take my residual and regress it on x and get the answer that the direct effect of x is 0, which is the right answer. So it also gives me the right answer. And appealing thing here is that here we only have to model y given x, k, and L. Okay, so that was actually the talk for a continuous response. But can this be generalized into where the response is an event time, a censored event time? And yes, it can, at least if you are willing to work with this model. So if we have an additive hazards model, so this is the old additive hazards model. So we have an additive effect of x, L, and k, and coefficients here that are actually allowed to depend on time. So that's one benefit of this model. There are some drawbacks also, but one benefit is that the coefficients can actually change with time. It turns out that it is not so straightforward to do the generalization. There is something about risk set selection, but let's go through it. So so I use this notation, capital psi, for the accumulated effects. So that's the parameters that you can estimate in this model. And here is the counting process. So n of t is the counting process. I'm sorry for that. Not much of counting processes, so relax. And this is the risk indicator. Okay, so the parameter that I would like to estimate, I call that gamma x of t. So that's the conditional mean of my increment of my counting process, given my counting process history, and given that I intervene on x, and I also intervene on k, keeping k fixed. And then I subtract the same thing where I put, so x should here be put to 1 and 0 here. So that's the direct effects on the counting process of x, keeping k fixed. Another way of putting it is via the survival functions. So putting x to 1, keeping k fixed, and taking the ratio here with where I put x to 0, is the exponential of minus the integrated version of this parameter. This may depend on k. It's not clear whether it depends on k. For the moment, I assume that it does not depend on k, and it actually turns out not to depend on k for this model. But it's not clear from this. Okay. So I will try to mimic what Stein and co-workers did for the continuous response case. So I will work with so I think of the increment of the counting process as the response, but I will work with that increment minus the effect of k in that model. So that's the residual from the early paper. And then I would like just to regress it on x. And I hope this will give me the direct effect parameter. So that's the idea. But let's first calculate what the direct effects parameter actually is, because it can actually calculate it. So if I have my own additive hazards model, and I postulate that the intensity or the hazard where I intervene on x and k has this expression. So I have these terms from my original model, and then there is a correction term as there was in the linear case. And this correction terms has to do with this expression here, where it's something about the distribution of L given x. And I think, so maybe I'll show you just one calculation, because then you'll see how this works. So the only thing I have to work with is the G formula. And the G formula, so this is the survival function where I intervene on x and k. And the G formula tells me that, well, you can work this expression out using this one here. So I need the distribution of x, of t given x, k, and L. And then I have to marginalize over L given x. So that's the G computational formula. But this is not so hard to work out, because here I have my own additive hazards model. So this term goes out from this integration. And then I have just the conditional mean of this term given x. And taking log and differentiate that with a minus in front should give me the hazard. And it turns out to be this expression. So it's really rather basic calculations. Since here I assume that x is binary, I can write this parameter in this way. So exploiting that x is binary, you can see it's just linear in x. And of course here you can see that this could also be worked out for the Cox model. So I just have to change my expression here. Instead of using the old model, I plug in the Cox model. But it will be more difficult. So the nice additive structure here gets me that this expression here, I can take that out from the integration. That would be more complicated if I had the Cox model. Okay, so here is my direct effects parameter. So this is actually the parameter that I would like to estimate. And again, you can see that it's different from the parameter in the full model. So this was my parameter in my initial old model. So there is a correction term again, like we had in the ordinary linear case. So a naive analysis condition on L, X, L, and K will give me the wrong answer. It will estimate this parameter only. Okay, this is just a recap, I think. So I'll go directly to the estimation. So it turns out that this term here, so here is my residual. This was the original idea. Here I regress on x. Actually, I also take in the intercept. So z is x and the intercept. And here is x again. So this was the original idea, but it turns out that this will not have mean 0. I also need to plug in a weight So I need to plug in the exponential of psi k there. And one has to do the calculations there to see that if you wait with this, you will actually have a zero mean of this expression. So there is a change of the risk set when eliminating the effect of k. Okay, so this has mean 0, and if you integrate that, then you get the estimator here. So it's a counting process integral, and it also has a recursive structure in it because the weights here depends on psi k. So you can estimate psi k from the original old model. So you do that first. But it will also depend on previous values of that term. So you have to be a little careful when you work out the asymptotics, but it can be done. So I'll not go into details with that, but you can show that your estimator minus the truth converges actually to a zero mean Gaussian process, and you can estimate consistently the variance of the limit process. So we can do the needed inference. Okay, I thought I wanted to show you some results from a simulation. So here I have the case where I have x, l, k, and the unobserved u. So let's say that this is actually an additive model. By picking the distributions carefully, you can show that the model where you only condition on x, l, and k will also be additive, actually. But there will be a change in the parameters. So the parameters down here, the effect of x is given by this effect here, minus something that has to do with the effect of the unobserved u. And this is the one that you will be estimating if you do the naive analysis. And this up here is actually the true direct effect. So this is the one that we would like to estimate. Doing the naive analysis, you will estimate this guy. And here you can see that this one, I set that to 0.1. This one is set to 0.2. So this one down here is actually 0. So if you run the analysis, this is the naive analysis minus the truth parameter, then you will see that you have a bias. So this is at different time points because we are estimating a time-varying effect, although it's constant in this case. So I've calculated at different time points, and you'll see you have a bias here. So the naive parameter minus the truth is minus 0.1, and that's exactly what you estimate. Whereas the new estimator here is unbiased. And this down here shows that it actually also works the asymptotics. I'll skip the application because I wanted also to say something about what we are working on right now. So this work has been published, but we are now considering other problems within the same area, I would say. So one thing, can we handle this for the Cox model? Can we handle the more difficult problem of time-varying confounding? So what I showed you was handling confounding, but actually K and L was fixed at time 0. So it's more interesting to deal with the case where they are measured at a later point in time. So that's a more difficult problem. And can you also estimate causal effect when there is unmeasured confounding? It turns out that that's in some cases possible using the so-called instrumental variable approach, and it's quite popular right now, I think, using this Mendelian randomization technique. So there are lots of papers published about that in the medical literature right now. And I'm doing this together with Stein and Chetskin from Harvard and David Zucker from Jerusalem. So how about the Cox model? Well, I will use exactly the same technique. The only tool I have is the G computational formula. I just have to plug in the Cox model instead of the old model and work out the expressions. And it gets more nasty. But you can actually work it out in this simple case where X is binary. And it turns out that, so if I have the Cox model instead, this is the naive analysis will give me psi of X. The true direct effects parameter is psi of X plus a correction term again. And in this case, the correction term will actually depend on K. So that was what I fixed the intermediate variable on. It didn't depend on K for the additive hazards model, but it will for the Cox model. It will also be time varying because it depends on the baseline hazard function. So it will be time varying. But you can estimate it. So you can actually estimate it. And yeah, it's also possible to do the asymptotic. So in a way you can handle it, but the expressions are not that nice because of the exponential link. So that's what destroys the calculations. We're working on extending this to continuous X and also to handle background covariates. It can be done, but it will involve smoothing. I have an application of this, but I think I will just move on to the time-varying confounding case. So this is in a way a more interesting problem. So here we are considering an exposure at time 0, or a treatment at time 0, and a new treatment later in time. And of course you can have more than 2. But if we can handle this simple case, I guess we can also handle where we have more than 2. Here we have some confounders, measured confounders, L1 and L0 and L1. But we also have some unmeasured confounders, although they must not be unmeasured in the way that they are confounders for the effects of the treatment. So some would say this is the no unmeasured confounders, but they can be confounders on the effect of the L's on T. So that's allowed. Like I allowed the unmeasured U before to affect L, not K. So this is the graph that we would like to be able to handle. Can we estimate causal effects here of the treatments? Yes, it's actually possible. It's more complicated than what I just showed you, but it's actually doable to work out expressions, and you can also handle the large sample processes. So this is work in progress. Yeah, okay. I think I'll round up just mentioning that you can also work with this example where you have an unmeasured confounder here. X is the exposure. You can actually estimate the causal effect if you have a so-called instrumental variable. So this could be a gene, and then you call it Mendelian randomization. Okay.
Torben, thank you very much indeed. Obviously, this is challenging material and maybe challenging to discuss as well, but I'd like to open it up for comments and questions from the floor.
I have one picture here that is perhaps nice.
Well, can I start off and just ask you something about the use of the Ireland model? Obviously, it's an additive hazard model. It has the disadvantages that possibly in applications that's not necessarily what you'd most obviously assume is realistic, and obviously has the technical disadvantage that at least theoretically you have the possibility of calculating negative hazards and so on.
Exactly, yeah.
And so I wondered, in terms of using it in applications, whether those disadvantages are such that you would say that although it's a very nice methodological advance, it's perhaps not at a stage where you'd want to use it in practice, or whether you'd argue against that.
Well, I use it occasionally, actually to check whether there may be time-changing effects for the Cox model. So maybe I think of using the Cox model at the end, but to check the assumptions, or at least to see whether there is an indication of time-changing effects. The old model may be nice to run. You can think it of as a first-order Taylor expansion, so it should fit the hazard quite nice. And there are software around now to fit the model. But I don't think that this part of the hazard being negative is not a big problem in practice, actually. But occasionally you will see survival functions increasing slightly.
Thanks. Other questions? Yeah.
So the lack of dependence on K in the all-in model, but the dependence on K in the Cox model, is one or the other what you would expect in a physical application? Would you expect actually the dependence to be there? Which is more surprising, I guess, is the question.
Maybe it's actually a nice feature that it depends on K. So actually this was an application where I actually used the Cox model. So whoops, I have a graph here of the estimate of the direct effect. So there are 3 estimates because there are 3 levels of the K variable. And actually the most dramatic effect of the direct effect is for K equal to 0, where there should be no. So actually it seems as a natural result. So maybe it's actually a strength that it does depend on K.
Other comments? So maybe I could ask another one in terms of the your assumptions about your variable L, which seem to be saying that anything which related between your intermediate variable K and the unmeasured confounding factors U came through L.
Yeah.
That strikes me that in practice that's quite a strong assumption that you'd have such variables measured that any of the confounding which is unmeasured must come through this variable L which you do measure, and therefore that's an assumption of the method, sure, but again thinking about the practical application of that, presumably that is a major and important assumption. Presumably it's also an assumption which you can't really assess.
No.
And therefore, I just really want to open up that discussion and say, again, in practice, how would you start to at least think about or address those problems about what you're assuming about L?
Well, I think that you may, of course, use more than just one L. So so typically you may want to use several L's, but as you said, there is no way of checking whether, because we don't measure the U. So it is an assumption that you can never check. I really don't have a good answer to your question, but yeah.
Thanks, David.
Well, we heard this morning about citation counts. I have another paper with, I think, a citation count of 0. And that was published about 7 or 8 years ago. And there's a throwaway line in it, which is basically that these decompositions do apply to the proportional hazards model, although they, as you correctly say, they are very complicated form. But my approach to it was quite different. But the paper's in Biometric. Dare I ask, have you seen this paper? It's called On a Generalization of Cochrane's Formula.
No, I'm afraid not. But I have to.
Well, it's either wrong or totally incomprehensible, or both. But I think it's trying to do the same thing, but by a very different method.
Okay.
for non-time dependent. Oh, I don't know. I don't know whether the explanatory variables can be time dependent or not. I've forgotten.
Okay.
But I'd be very curious to know your reaction to the paper.
I will look it up and read it.
Thank you.
Thank you, David. I think the citation count of your paper might be going up at least to 1. It's an infinite increase in your citation count for this paper. Other comments, questions? Well, if not, can we thank Torben again very much for his talk? So I'd now like to introduce